Okay, in this video we're gonna talk about different ways to simplify certain radical expressions. So I'm gonna start off by trying to figure out what each of these numbers is. So let's look at the first one. The square root of 5 squared. Well, 5 squared would be a 25. And the square root of 25 would be 5. Since we mentioned in the previous video, the radical symbol is referring to the principal square root, meaning the positive one. So the positive number that squares to be 25 would be 5. Okay, next example, negative 5 squared would be negative 5 times negative 5, and negative 5 times negative 5 would spit out a positive 25. And this should look really familiar because we just did it. We get positive 5, the principal square root back. And so this is actually telling us something interesting. When we take a square root of a number and then we square it, we don't actually get back the original number. We get back the positive version of the number, meaning the absolute value of the number. So for square roots, we can say the square root of a squared is going to be the absolute value of the original number we started with. Let's see if the same thing holds true for cube roots. So the cube root of 4 cubed. 4 cubed would be 4 times 4 times 4. 4 times 4 is 16. And 16 times 4 is 64. And then the cube root of 64, you're asking yourself, what number times itself 3 times spits out 64? We just did it. It was 4. So the answer is going to be 4. Okay. The bottom example, negative 4 times itself 3 times. That's 3 negative signs. And 3 negative signs means we're going to stay negative. So instead of getting a positive 64, we're going to get a negative 64. So this is something that's interesting about both roots and powers. When we're talking about odd powers and odd roots, if we start with a negative, we're going to stay negative throughout the whole problem. And that's what's going to happen next. The cube root of negative 64, what number multiplied times itself 3 times is negative 64? Well, it would be negative 4. So for cube roots, we actually have something easier happening, which is the cube root of the original, the cube root actually spits out whatever the original number was. Cube root of 4 cubed spits out 4. Cube root of negative 4 cubed also spits out negative 4. Okay, it turns out the same thing is going to be true if we're talking about any even exponent and power and any odd exponent and power. So let me leave this for a second. You might want to pause, but I'm going to immediately start to erase. And write it as 2 cases, depending on if the power is even or odd. Okay, so we're going to use this in just a second. Our next example that we're going to look at is unrelated. I want to look at the square root of 1 plus the square root of 4. And I want to see if I get the same answer if I try the square root of 1 plus 4. Okay, so the top. Square root of 1 would be 1. What number times itself is equal to 1? It would be 1. What number times itself spits out a 4? That would be 2. 1 plus 2 is 3. 1 plus 4, on the other hand, is 5. And square root of 5 is equal to some weird decimal. It's not 3. That would be 2 point something. That's a guess. Don't write that down as a fact. Type it in a calculator if you want to be sure. But it's definitely not 3, is the point. So we have to be really careful taking square roots anytime there's pluses or minuses. Minuses is going to do the same thing. Square roots do not like those operations. They're just not going to work out the way we expect. So we have to be very careful that we don't split up square roots into individual pieces. And the reason this is going to be tempting is if you see something like, I want to just say it's the square root of a squared and the square root of b squared, but it's not. That's the way what this is saying. We're not going to get the same answer. do know what this expression by itself means. A square root of a square we just talked about would be the absolute value of the inside number, but the right-hand side and the left-hand side aren't the same, so it's not particularly useful. Okay. Let's erase and try a different one. I want to try a way that we can actually compute a sum of two radicals. So I'm going to take the square root of 32 and add it to the square root of 200. Okay, if you sit there and think for a while, you're not going to be able to come up with a number times itself that spits out 32. It's not a whole number. Same thing for 200. It's not a whole number. So we have to see if we can maybe write these two in simpler ways in order to get something out of this. Unless we had the calculators available to us, in which case we could turn everything to a decimal and this would be a silly question. It's an easy one. But let's just try it without a calculator. So let's see. What we're going to try and do is write each of these numbers inside as a product of simpler pieces. Because even though I just got done saying that square roots don't like sums, I had this written with squares. It's also true with just the numbers themselves. However, this same thing for products is going to work out. And just like the two rules we have up above, it's going to be the same even if I was talking about cube roots, fourth roots, any kind of root. Okay, so I want to try and split these two up into a product of simpler things because it turns out, for some reason, products and exponents work out much better. So let's see if we can do that. One way to think about it is, do you know a perfect square that divides evenly into 32? And you probably know a couple of options. 1 divides evenly into 32, 4 divides into 32, and 16 divides into 32. And of those, probably the biggest is your best bet. That's one way to think about it. That's not my favorite way to think about it because sometimes it's hard to figure out what's the biggest square that divides in evenly. Instead, I'm going to talk to you through a different way to think about it. So let's try and break each of these numbers, 32 and 200, into prime numbers, because it turns out prime numbers are going to be easy for us to manipulate. So let's write 32 as a product of prime numbers. And you might already know what 32 is as a product of prime numbers, but I'm going to show you this weird way, and it'll be fun. So let's see. Can you write 32 as any product? Let's see. It's on my memorization table for multiplication as 4 times 8. So let's write it as 4 times 8. You might have written it as 16 times 2. Totally okay. What we're going to do now is take each of those numbers and split them up into products of other numbers until we get down to prime numbers. So let's see. Can you write 4 as a product? Yes, it's 2 times 2. Can you write 8 as a product? Yes, it's 2 times 4. Okay, and then we just keep going. We're going to make kind of an upside down tree. Let's see. 2 I can write as a product, but only as 2 times 1. So once I get down to prime numbers, I'm just going to leave it like that. I'll circle it and say, done with that leaf of the tree. 4, however, I can keep going. 4 is still a product. It's 2 times 2. And so all this mumbo jumbo means that the number 32 that we started with is actually the product of these leaves. I've just continuously broken down into product of simpler things. Square root of 32 is the same thing as the square root of 2 times 2 times 2 times 2. There are 5 2's. Okay, let's try the same thing for 200. And again, your tree might look a little different than mine. That's okay. We're just trying to write any way to write 200 as a product of whole numbers. I'm going to pick 20 times 10. You could also pick 2 times 100. That's okay. And then each of these numbers further split it up into a product. So 20 is 4 times 5. 10 is 2 times 5. circle all the prime numbers because we're done with those, and then keep splitting. So we have 2, 2, 2, 5, and 5. So 200 written as a product as 3 2s, a 5, and a 5. Okay, now I'm going to try and combine a couple of these rules on the right. One of the rules says if we have a root of a product, we can split it up into a product of separate roots. Okay, I need to figure out what's the best way to do that. This is the best way to do that. We want to take a square root of squares. We want to take a cube root of cubes. So let's see, we're taking a square root. We want to look for squares. Well, there's a square. 2 times 2 is a square. There's a square. 5 times 5 is a square. 2 times 2 is a square. 2 times 2 is a square. So I'm pairing the numbers up because we're taking a square root. If the original problem had cube roots, we'd be looking for triples of numbers that were all the same. So we're looking for a 2, 2, 2 or a 5, 5, 5. Okay, let me erase my mumbo jumbo trees, which are just trying to figure out ways to write 32 and 200 as a product, which we have done. And now I'm going to use the bottom row on the right to say, okay, this is a product of hopefully simpler radicals. Okay, and several of these we should be able to simplify, namely this rule. So the square root of a number squared should be just the absolute value of that number. So this should be the absolute value of 2. Absolute value of 2 is just 2. This is also going to be a 2. This is also going to be, oops, that one doesn't. That one's just going to stay alone. This one is the same as all these ones. It's going to be a 2. Square root of 5 squared would be the absolute value of 5, which is 5. And let's see. So 2 times 5, I can just call that a 10. 2 times 2, I can call that a 4. I'll put the numbers up front. And now we have something magical happening, which is from the original square root of 32 plus square root of 200, we said at the very beginning, we can't add those together. We can't say that's the square root of 232. It doesn't work out that way. Now, however, we have 4 of something plus 10 of something. 4 of something plus 10 of something should be a total of 14 of that something. So this is our distributive property. It's how we combine like terms. So once we have it as looking like the same radical, so this isn't always going to work, but for this example, since it was square root of 2 as our simplified version of the radical in both cases, they are like terms. We can add the 2 and say 4 of something plus 10 of something is 14 of that something. And then this is a much simpler way of saying that original number, square root of 32 plus square root of 200, should be the same as 14 times the square root of 32. I strongly suggest that you on your own type into a calculator this expression and this expression and make sure that you're getting the same decimal answer. You should be, but let's double check. We can always double check our work.